Great. Thank you, Chris, for introduction. And good afternoon, everyone. I'm Minghan. So, as introduced, today I'll talk about 3D robot vision for structured world understanding. Let's get started. I think we are kind of in an era of where our robots are driven by data, where like both industry and academia are pouring a lot of efforts in collecting data from teleoperation and demonstrations. And we see a lot of and we also see a lot of good works that comes out of this strategy. For example, like I think basically every week or every day you see some impressive demos. Like this is already just a few weeks ago, but already feels like long. But we want to see this pixel to action method strategy made a lot of progress. Like with this pretty accurate, precise textures and even some dynamics tasks just from pixel to actions. So it's great that a lot of people reach some are working in this direction. But is it the end game? Is like is that all we need? And actually things will become simpler and maybe it will just be solved in a few years. But if you think about where we may want to deploy our robots in, like this very harder environments or even this disaster rescue, where it's very unstructured, it's complicated, and it's likely out of distribution for your data collection. And if you want your data to cover such scenarios, I believe there's a lot of work that's very tricky to reach that goal. So how to bridge this data gap or how to go from there to here, like we also have this this argument made by Ken Goldberg, who visited us a few weeks ago. Like we may need 100,000 years of data gap in robotics to bridge this gap, which is he refers to the data used to train GPT level of LLMs. And so hopefully we don't want to wait that long. And today I want to talk about how I think 3D could be one of the solutions that can bridge this data gap. Because naturally, the real world structures live in 3D and they're well represented in 3D. That includes geometry, physical interactions, physical properties, and all the dynamics information. And they can be very obscure or convoluted in image space, pixel space. And with this, if we actually have this 3D understanding, that can make a lot of paradigms easier or more data efficient. For example, then we can directly be used in model-based planning and control. This is actually a work done by my lab mates at their lab. This push anything is about solving this multi-object planar pushing if you are given this object geometry and poses. Of course, this 3D information will be very helpful in real sim to real, where all these diverse real-world scenarios can be poured into simulation where learning is more scalable. And then if your policy is based on top of these geometric or 3D notations, then you don't suffer from those pixel rendering sim to real gaps when you transfer that to real. Also, I think a field that has a lot of potential that is learning from natural videos. Today, we learn from YouTube videos in a very superficial way. For example, this 2D point tracking, key point tracking. But if you can actually understand the physical interactions, the geometry in there, that can unlock a lot more potential just to learn from in the WOD videos, which we have a ton of. Also, it's also promising that like how do we get these word models or imitation models with better intuitive physics? I think a notation of 3D and physics is natural there. Although and obviously today, even with very big models with pixels, it's still very tricky. And we used to think that way, but we don't have good 3D vision capabilities. That's kind of what held the robotics back, and people turn to this end-to-end methods. But if you take a look at what happened in the 3D vision community recently, there has been a lot of progress, very impressive. For example, this VGT model for image depth and correspondence matching, or generative models for 3D assets, like the recent we have also SAM3D, this kind of work, or video generations. They are they show that this capability of geometric understanding is making a big progress there. But we don't yet have a whole package that actually understands the real world structures I just mentioned that includes not only geometry, but also physical properties, dynamics, how things interact, and basically how events unfolds in our real world. We're not quite there yet. So today, I'm going to talk about my attempts in this direction about using developing 3D robot vision that understand the real world structures. So this is actually it should be a virtuous cycle, meaning that it should go both ways. On the one hand, my goal today is to understand the real world geometry and dynamics. On the other way, the problem formulation itself, the domain should inform us useful insights and tools. And I'll be talking about physics and symmetry as the specific lens I'll take in dealing with this problem. So my talk will have two parts, physics and symmetry. And let's get started with the first half, where I talk about how physics play a role in 3D vision, specifically occlusion robust 3D vision by joint reasoning of geometry and dynamics. So our real world is often cluttered. If you see a kitchen picture like this, you'll probably guess no real people living here. Everything is so clean but if you have a kitchen like this, I respect that. I admire that. I would say good job. But probably more typically, you will have a kitchen like that where things are more cluttered and you cannot have a good view of everything out there. Or even maybe after Thanksgiving, you have a kitchen like this. And so the things are cluttered and they kind of just created this not easily visible, but things are kind of all touching each other and creating these weird configurations here. But actually, human can understand such cluttered scenes despite occlusions. Like a video, this is a slow motion video. Like you put the plate on these piles and then this fall off. Then you can tell that you have how many plates. There are some spoons and utensils down there, and you also have a round bowl below it, even though we just see a small corner of it. And we actually in research, we coined this simplified setup where we also have a lot of occlusions. So here we are interested in something that's also behind occlusion. Here it's a box, it's a tabletop scenario, but we never see the full box. And we have it's occluded by a pile of things in front of it. Here is books, but we have some robot interact with it. And even with these occlusions, you can tell what happened. The robot arm is just kind of pushing the boxes on the table. So how did human can understand this scene despite all the occlusions and imperfect vision? So I made a simple this flowchart. If you understand this image or video just as a projection of geometry coupled with pose and trajectory, then the reverse process is basically just visual tracking and reconstruction, typical 3D vision tasks. But I think in these examples, there is another link that is the object's pose or geometry or trajectory is not random. They don't just float in the air or penetrate each other. Actually, they're governed by these physical dynamics rules. And leveraging this dynamics rule to reasoning is sometimes we call this modeling. So actually, we human implicitly has the capability of reasoning the geometry of the scene with this pose and trajectory optimization. And in the first work I introduced you, we will leverage this perspective and show how this, including this missing link, can enhance 3D vision and make us understand these clutter scenes. Here is a preview of what it looks like. So first, this work is called Vysics, and this is a collaboration between me and Bebe, my lab mate. And on the left and right is a comparison of what we can have with pure vision perspective versus what we can have if we take this physics perspective into consideration. The green thing is the overlaid, reconstructed partial object of the box with this trapped pose. You can see it, basically you can only see the visible part. It's a small part, and you're missing a big part of it. And if you take this modeling perspective, you know that something is pushing it. Here we have the robot arm is pushing it. And then we can actually recover the full object by making sense of the trajectory, but making sense that it is being contacted by the robot end effector. Thus, they must be in touch. Thus, it has to be bigger than what is visible in the image. That's the idea. How is this exactly done? I'll show you a brief diagram. So the first part of this system is basically just pure vision-based tracking and reconstruction. You take a masked RGBD video, the mask is on the interesting object, and then we can get this visible geometry and object pose tracking. And then the second part is this physics-based model learning, which takes this object pose and the robot pose together, and then you learn what object model can explain the observed motion. And that gives you this estimated geometry that makes sense in physics. We call this feasible geometry. You can also recover other properties like inertia. At the end, these two estimations are merged together into an integrated geometry, which both leverage the visible details and also make sense in terms of the contact dynamics. And I'll show you how this, since here, the vision part is kind of given. So we'll show how this physics actually plays a role and allow us to estimate the geometry just from this physics onset. Here, I draw this blob in purple. This looks like nothing because it is something we want to optimize. It will be initialized as some object that's not true. And we have a robot end effector, which is that thing, and then we also have the ground, which is the flat surface. And then you observe some motion. That is, this x is the trajectory. That is, the object is moving to the left. So now what happens? Well, first we'll create a sample of the shape. So basically, we'll sample some direction, and then we'll get this furthest point. We can basically treat them as points with normal that represent this shape. And then what happens in this physics-based inference is by optimizing this cost function. This cost function includes two parts. The first part is trying to explain the observed motion. The F is the dynamics model, the X prime is the next state. So by minimizing the difference, we are trying to learn the model that explains observed motion. The second part is trying to be compatible with the contact model, because we actually know, we have knowledge about how contacts happen. For example, things shouldn't penetrate. For example, a contact force cannot be exerted as a distance. You cannot just push it through the air. So those are the information, the knowledge we know. So now in this optimization problem, we're trying to achieve both goals. So how do we do this? We will, you can see the first step of this optimization is by estimating contact force, which is the lambda terms here. You can see there in the loss function, it is a bi-level optimization. There's a minimization of a lambda first. The lambda is contact force. So first, we'll estimate the contact force that explain the observed motion. Here, the object is moving to the left. So we should estimate a significant lambda 5 force here. And probably the other force are small. We also have it supported by the ground. So this contact force should also be substantial. So you will first estimate the contact that made the motion happen. And then they will induce a gradient on the shape. Why? Because now if you estimate there's a contact force, then they should be in touch, but they're not in touch. Therefore, this gap should be minimized. And this is the driving force for the geometry optimization. On the other hand, we also have the visible information from the RGBD video. And that part is straightforward. We basically just take the nearest point on the current shape estimate and try to bridge the gap between the visible point and the current estimate. So this allows us to leverage both vision and physics information. Any question here? Yeah.
Do you assume contact forces on all the vertices as on the contours of the object? Because I think you put lambdas for every S in this convolution.
Yes. So we will sample a lot of points. It's actually more than 5. So we'll sample like hundreds of directions.
I see.
So they will, and then
come with a contact force.
Yes, each one comes with a contact force. Yes. So then the experiment setup is like this. So we are basically using this robot arm to to play with a bunch of objects we found in the daily office in the lab, or at home actually, not in the lab. And then we can see there are some pushing, toppling, pivoting interactions with the object, and we try to use this to estimate the 3D model of the objects and all the dynamics from such videos. And this is what it looks like. The video, the first row of this videos is the RGB input overlaid with the object estimation. The 4 columns are from the physics, our work, and vision only, and physics only. And the last row is what if we put the boundaries object in. And I forgot to say the second row of here is a simulation, basically to test whether the physics actually makes sense. We put the object in the simulation and replay the robot actions to see if the outcome is as what we observe in the real world, which can be a bit chaotic because which can be not super accurate because this open loop simulation of contact-rich events are naturally divergent. But you can see that with this vision and physics combined together, the reconstruction is just it just recovers the whole extent of the objects. And despite that, it never sees the occluded part compared with the vision-based method. It also has much more like sharp surfaces compared with if you only use physics to optimize the shape. Question?
There are some directions where the geometry can be extended without, like your physics cannot tell if the geometry is longer in this way or shorter in this way. Are there null space directions?
It's like you're saying that the content may not, it's not dense, so it may not reveal information about some part of the geometry.
Okay.
Yes, that can happen. Actually, that is also one reason why you see that the reconstruction is like, although it's more complete in terms of the ballpark shape, but it's not accurate by any like modern 3D vision standard, right? Because the contact points are inherently very sparse. So they are not, they do not provide the rich information to confine the shape.
The other question is,
it's not real time. So it's like take this video, it has to do the visual reconstruction first and then do the physical optimization and then combine them. So it's not a real time system. Yeah.
I don't get what happens in the simulation. Okay, the first one, you just give a mesh, right? Probably.
Yes, they give a mesh.
Yes, but no other problem.
We give the inertial property as well.
Yeah, but friction or anything.
Friction is preset.
Okay. And in the second one, also a mesh, but derived from the bundle there.
Yes.
Yours, the PLL?
In PLL, it's a physics only method where we don't have the vision signal. We purely use the physics-based optimization with the contact to estimate a shape. So it has no...
You don't use the physics of the simulator.
We don't use the RGBD observation. We only use the tracked pose. We basically only have the...
Where did you use the lambdas?
Where do I get the lambdas?
No, where do you use the lambdas in these videos?
The lambdas are used to in the optimization. It helps us reconstruct the shape. The lambda does not occur in the evaluation of the simulation.
All of that is a shape reconstruction because the minimum was not with respect to shape, was with respect to lambda in the previous step.
The minima is with respect to lambda, but the loss function is with respect to the shape.
Oh,
so we minimize the L.
Minimize L.
Yes.
Find S.
Yes, we find S, but when we find S, we need to minimize L in the inside loop. So it's a bi-level optimization.
Okay, yeah. So then in the whole bottom row, you only give shape, right?
Basically, yes. Essentially, it's basically shape.
So this is really an estimation problem, not a control.
It's not a control problem. It's a replay. Yes,
Yeah, exactly.
yes,
Very nice. So this is how to use physics to estimate geometry better, and the geometry estimate physics better.
yes, 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 yes.
Very nice.
Thanks. Okay, then I'll continue. So this is like some figures showing.
Sorry, and the FS was a network or explicit dynamics?
Which one?
FS. F sub S. Your dynamics were a network or in the previous slide?
In the previous slide.
The previous slide. The dynamic model.
The FS is a network or a
The FS is not a network. FS is basically a simulator. Basically we have a simulator under the hood for the for the physics model, for dynamics model. Yes. But we learn the properties, including the shape, the like inertia kind of things.
like Monchoko or
It's a district-based simulation. Okay, and it's more accurate than just pure vision in both geometry and dynamics. But as actually we just discussed, like this reconstruction is also, you can see that it's accurate in ballpark, explains the dynamics, but it's not accurate in terms of visual quality. It's actually pretty rough. And the reason is that we just discussed is the contact dynamics is informative but provides very sparse information. And naturally, we actually bring another thing into the figure. That is, we actually, as people, we know we have understanding of how typical objects in daily life look like. And that means we can leverage this kind of prior also when we try to understand the world. And such generative priors of how typical shape looks like is dense but distributional. So actually, these two perspectives are kind of complementary. And I'll show you, by merging these two methods, we can address the problem that the rough reconstruction. So the idea is basically a different figure of the same idea. With the phase space inference, as I just showed you, it provides you sparse understanding of the content. And on the other hand, if you have understanding of how typical like a milk box look like, that gives you some good prior knowledge. And by combining the two, you can have good 3D reconstruction that is accurate in physics and also visually higher resolution. So such priors in 3D generative models, like here I draw a trellis or a model 3R, which basically can take image or even uploaded image to reconstruct 3D, they are typically diffusion models or flow models. And how these models work, as a very brief recap, I believe most of you are already very familiar with this, is that we start from some initial distribution noise, like Gaussian noise, to the data distribution, and the flow is mostly governed by this gradient of the log probability of the probability path. And how do we incorporate this physics in this structure is by guided generation. So now it becomes a conditional generation problem, where now your target data distribution is your data, the shape, given y, which is the physics information. And now the flow will be mostly governed by the gradient of log posterior probability. And we can expand this term into basically the prior plus a likelihood term. So now basically the difference between a 3D generation and physics-informed 3D generation is the likelihood term. And that likelihood term is typically, we can formulate that as a loss function. So now basically the problem becomes, how do we formulate a loss function of a 3D generation with respect to some physics observation? And in our specific problem, we just treat this physics as contact points. That's our form of physics understanding. These contact points can come from the prior work I just showed you. So how does this work? I first show you how the 3D generative model works. Specifically, we use this trellis model, which is a volumetric model. So it takes an image. So here I use some syntactic image as input, like uploaded. and start with some noisy volumetric features. And it tries to, it goes through this DIT model, which then gives you this volumetric occupancy grid as the shape. But now we have sparse contact points like this P, a single point. How to guide this dense volumetric grid with sparse points is the question here. And the
P is the contact points or the lambdas are the contact points?
P is the contact point. Yes, the lambda in the previous slides are the contact force.
Yeah.
So the points with significant contact force, we treat them as contact points. Yes. So this volumetric grid is very dense, but the points are very sparse. So now this, if you directly, for example, just try to maximize this occupancy at this point, it just won't work because it's too sparse. So how do we deal with this problem? We use a self-reference loss strategy. The idea is that we will first generate the shape based on the image without any guidance. So we will have, this is like a template generated by the model itself. And then we have the contact point. And for this contact point, we will find the nearest point on the occupied grid. We call it Q. And then we will find a neighborhood around Q. We call it the reference, the local reference. And then we will rerun this guided generation again. But now we will apply this guidance. And the guidance is basically trying to duplicate the neighborhood around Q at the neighborhood of P in the guided generation. We're basically trying to copy the neighborhood from the unguided template to the new location. And this strategy will provide a dense vision because it's more than a single point, but it's also with minimal bias because we're not pre-imposing what the contact part should look like. Basically, the reference is generated by the model itself based on its understanding of the shape. And you may think it's kind of rough, but this, like how does this copying just directly work? But actually, this is inspired by this drag-based image editing literature. So 2D image dragging literature task is basically you want to, for example, you want to drag the nose of the line to a different place in a 2D image. And one way to do it in diffusion model is basically add noise and then denoise. And in this process, when you denoise, what you'll do is you want to match the target neighborhood feature with the source neighborhood. Basically, you want the neighborhood feature around the point P in the denoising path to be similar to the neighborhood features of around Q in the adenoising path. And it is rough, but actually the diffusion model will figure out the rest. We'll try to make sense of how to blend this patch with the surrounding environment. So our approach is basically similar to this, but we don't have a source image. The source is obtained by guided generation, and we apply this strategy in 3D. So then this, how it works, I show you in a real data. It's a bit laggy. So basically with that occluded milk box, you'll first take this into this unguided model. We use a model 3R. And then this will give you a pretty high quality shape. But there's no way that this generated shape is actually exactly the shape because it never sees the other half. You can see there's a misalignment. The shape is not that accurate. But then we have these contact points from Vysics. And then we'll take these contact points and sample some of them and use them as the guiding point to rerun this embodied 3R. And then the resulted generation will be both high quality, similar to the unguided one, but also compliant with the contact points.
I'm confused because there are no physics here. Contact point is just the point is just close. It's a geometric relation. No force or anything. There's no physics here.
I just use points, yes. I just use points.
Just geometry.
Sorry, what?
Just geometry.
Just geometry, yes. Yes, so here we're basically taking the geometric understanding of the contact points in this 3D generative model. Yes, we didn't consider the force in this work.
How do you detect the contact point?
The contact points comes from the previous work, from Vysics.
Oh.
Yeah. And also, we also did some syntactic data. Then in this GSO data set, we just sample points on the surface and treat them as contact points. So we sample the points as contact points, and then we use this to do this conditional generation. And the result is we have these two rows. Basically, the first row is the unguided one. The second row is the guided one. The point, this red point or pink point, is one of the contact points we give as a condition. And the last column is the arrow, where blue is a lower arrow. So with this point as the condition, actually we can get the shape estimate that is more accurate.
I'm confused between the chicken and the egg here.
Yeah.
You want to build the prior model for shapes, right?
The prior model for shapes is there. It's like a pre-trained model.
The pre-trained model.
Yes.
And you want to make it better.
Yes, I want to make it better in my specific scenario. Yes.
For your specific scene.
Yeah.
That's why you run first the PLL.
Yeah.
And you use PLL as guidance in the diffusion.
Yes.
Okay.
Yes. Okay.
And then you go back to the PLL again.
We didn't, but I'll talk about it. It's like it's not complete, I think. Yes. So basically, the takeaway here is that robot vision is an embodied task, both in terms of purpose and approach. So you should consider interaction as one of your goals, and that also helps your estimation. And joining the power of data in physics has huge potential. And this is the figure that I just showed you. But you can see that if I want to add here is that even with this system, it's not complete because most of the blue arrows goes back to geometry. But the 3D understanding is not only about geometry. Actually, the post part here, only from vision, can be kind of fragile. The post tracking, the trajectory, pure from visual it's not ideal. So actually, one of my future work, what I'm going to work on is actually we want to jointly do the reconstruction and tracking and combining visual cue, physics, and data prior. So data prior should also not only just learn a 3D geometry model, but also learn a prior model for post and tracking and use that in the joint optimization framework. Okay, and now so now I'll come to the second part, which is about the symmetry. And I will talk about symmetry how I use symmetry for 3D geometry and dynamics learning. So symmetry is basically are the things that don't change on certain transformations. That happens in physics law, like you're in different rooms and physics laws are the same. That happens in geometry, things change their pose, but they're of the same shape. And that happens also in action. For example, if your environment transforms in some consistent way, then your action can also just transform in that way, and that will work. And equivariant learning captures this symmetry. It's one way to capture this symmetry. Basically, equivariant models are this phi model, which is commutable with the transformation. Basically, you have an input. You either you just get the feature and then transform the feature that's equivalent to you transform the input and then get the feature of the transformed input. If they're equivalent, then we call this phi equivariant model. And a very toy motivated example of how this thing can help, I will use a point cloud restoration problem where we have two point cloud of a guitar and they are rotated by some degree, we don't know. And the permutation is also unknown, meaning that we don't have the correspondence between the points. And typically, you solve a correspondence problem, you solve the registration problem by finding the correspondences and match them. But if you have these equivariant features, that means that just extract the features, and the features will live in a space that also carry the same rotation. And now, if you want to solve for the rotation, just apply a simple SVD on the global equivariant features, and that directly gives you a rotation that also applies in the input space. So this is an intuitive example of how equivariance work and how these features can be handled. And my contribution in this area, I have two axes. So first is in terms of algorithm and applications. So I'll first talk about 3D geometric learning, where my contribution is mostly by improving its efficiency. And then I'll talk about its application in dynamics learning, where I'll talk about expanding the scope of symmetry-aware learning from compact groups to some more general notations, symmetries. So equivariant learning is known to have some computational challenge because they, a typical approaches of approaching this is by lifting the dimension or use stable features. Both comes with computational overhead. And one way to intuitively understand this is like if you want to do a SO2 group convolution, then the straightforward way is basically just you have a convolutional filter and just rotate the filters all the ways in SO2. And your output feature dimension will be x, y, plus another dimension, which is theta, the SO2 dimension. And you can see that this lifted dimension that records everything in SO2 brings computational overhead because you have one more dimension of features to hold and compute. And you can see that in SO3, this can be even bigger problems. So if you want to do this in SO3, one way to visualize this SO3 is consider it as the sphere. And at any point on the sphere, you also have a rotation around the axis. That is composed of 3 dimensions of SO3. Or if you discretize that, that can be discretized into this icosahedron. You have every vertices, and on every vertices, there are different directions. So if one way to do this SO3 equivariant learning is by learning features defined on every of these arrows on every point. However, it may not be necessary. Or we can learn features only on a sphere. The idea is here, like we just look at the sphere, for example, our Earth. Then all these 6 have different patterns. Basically, by looking at an image of the sphere, you actually can figure out the orientation of it. That means that to tell SO3 formation, you don't need features defined on SO3, but you can use the lower dimensional features. You only need the features on the sphere. That is enough for you to tell SO3 related information. And that is exactly what we did. Instead of, in this work, Ethiopian, instead of learning a feature on every SO3 element, we just learn features on this S2 sphere. And then we can recover all rotations by just finding the correct permutation. Because, for example, you just take all these different features and put them together. Every orientation will correspond to a different permutation. And that is enough for you to understand SO3 features. And with that, that leads to computational saving. Because if you deal with the vanilla SO3 equivariant convolutional network, that means you're lifting a dimension which is called a size of 60. But if you just lift to the sphere or just lift to the icosahedron's vertices, that is only 12. So that represents rough 5 times of saving in terms of feature map size, and in practice a little bit even more in terms of computation. So this work basically reduces the
what is the action in the cathedral case?
Sorry, what is the what?
So when you have the reason it is in the 60,
Yes.
is not that we have 60 vertices, it is that the possible rotations are 60 rotations.
Yes.
How many are the possible rotations in the dodecahedral sample?
There are a lot of possible, like there are basically 12, right? Like 12 times 11 times 10. You can have a 12 number of possible permutations, but you don't need to enumerate them all because every single rotation corresponds to one permutation. So you only need to enumerate the 60 and find what permutation is the best. So every rotation is a
group. How many group elements do you have? Because when you do the convolution, it's really to create copies for every.
So we have 12
for every group element.
We don't have features for every group element now. It's a homogeneous space convolution.
Okay, it is back on the.
It's S2. It's only S2. So we only have 12 elements to track. Yes. So this leads to like significantly lower memory consumption and also much faster inference speed. And my collaborators apply this framework and kind of later apply on different tasks. For example, point cloud registration is a natural work. You can see that this this equivariance, especially with high efficiency, can allow more robust registration with like low overlap and large initialization error. We also apply this for the radar odometry. Like the radar points are much sparser than like LiDAR point clouds. And the different thing is that they now also have this velocity features attached at every point. And we can actually also manage to incorporate this equivariant structures in there. And I also have another work that apply this method in 4D panoptic segmentation in this self-driving scenario. And at the time of submission, which is already near 2 years ago, it was ranked #1 and stayed there for quite a few months. Then I'll talk about dynamic learning and how I expand the scope of symmetry to realize that. So now we'll talk about the symmetry is a little bit different from what we typically think about. So a typical thing, if we think about points on the transformations, they're associated by this left action. Q equals to TP. This is pretty straightforward. But what if we are trying to understand the transformations under change of basis? Basically, we want to understand how the same linear transform is represented in different bases. That is actually a conjugation action. And we will talk about this conjugation symmetry in the following section. And why do we care about this? Because these transformations could be, for example, it's just poses like drones or any factors, maybe. And then, so to set up the problem, we will use this phi-s as the operator to represent this conjugation action. And then, because this is a matrix form, which is not handy to deal with, we'll use a linearization to put everything back in the vector space. And this conjugation becomes this adjoint action, which is actually of the same form, but now we're dealing with input as vectors. That is the Lie algebra elements. And further, we can actually convert this adjoint, which is this conjugation form, the sandwich form, into a matrix multiplication form, because the adjoint action is actually still a linear operator. So now at this point, we're dealing with a symmetry that is very similar to just like point transformation, left action symmetry, but just with a different representation. This S here is not just like typical transformations, but this adjoint operators in this matrix form. But this similarity in terms of form allows us to deal with it with like existing structures. Here we are borrowing this structure from vector neurons, which is very typical, which is very wide used equivariant network. The idea is very simple. You have points that are with features that are 3D features, and you multiply your weight matrix on the left and your rotation multiplies on the right, and they don't interfere with each other. So just by augmenting MLP layers from point features, from scalar features to 3D features, that allows you to deal with SO3 equivariance. And you have inner product, which is rotation invariant, and that serves as a nonlinearity in this problem. And with that, we can directly transfer this form into this linear, where we are dealing with not 3D just point vectors, but now we're dealing with Lie algebra vectors that is m-dimensional. And the rotations becomes adjoint actions. And the invariant operators will change from inner product to this Killian form, which is a bilinear form that is also invariant to adjoint actions. And in SO3, that is actually just equivalent to inner product. So it is a generalization of inner product space to this adjoint representations. And furthermore, with this Lie algebra perspective, that allows us to use even another operator that is this Lie-Bragg operator, which is also invariant to adjoint actions, meaning that we have more expressive nonlinearities in our library. And the good thing about taking this Lie algebra perspective is that now we are beyond just compact groups. Actually, because we are not relying on this inner product, that means that we don't need to preserve this rigidity. That allows us to, this bilinear form, Killing form, allows us to deal with semi-simple algebra. And with recent work, we extending to reductive algebras. Basically, that means we can deal with like SL groups or even GL groups. GL groups, just general linear transformations. This can also be modeled with this Neurons framework. And we apply this in dynamics learning. So here is a Euler-Poincare equation of a rotating rigid body. We want to learn the rotating dynamics of an object by observing its trajectory. The idea is to given a trajectory, and then we want to learn the vector field, which is given the angular velocity, learn its time derivative. And from there, you can use the ODE solver to integrate it to predict the trajectories. And actually, just by even learning from a single trajectory, we can learn this vector field with equivariance. And we can actually reproduce this dynamics almost perfectly. And with this extension to this general linear group, that also gives us a new way to process covariance matrix. Because covariance matrix is, if you think about it, it is a matrix that is, they're not 3D vectors. They're kind of, when your system rotates, the covariance matrix actually go through this conjugation action. And now we can embed this 3x3 matrix into this general linear group space. Treat the SO3, treat the covariance matrix as a general linear transformation. And then we can use this framework to model the covariance matrix in the exact SO3 equivariant way. And this allows us to do much better neural odometry. As in this table, this reductive neuron achieves the lowest estimation error in this neural odometry test. So I think, one thing I want to propose here, I don't have a concrete thought, and I welcome your opinions on this, is this non-rigid symmetry can be potentially very helpful in robot parser learning because it can generalize this rigid body transforms to this multi-object setup where rigid body transforms almost never hold. For example, if you think about this task of you have 4 objects, like these blocks are objects, and you want to, you have the robot on one, you want to approach it. You learn a parser here, and then you want to generalize this to a different form, where everything is moved, but they are not moving in a rigid way. There are actually some deformation. And it is possible that we can use this general linear transformations, which are actually deformable, not rigid transformations, to approximate this scene change. And such non-compact symmetry tools can be handy in realizing this kind of generalization. So the takeaway here is that symmetry is a key to generalization for understanding the 3D world. And specifically, non-rigid symmetries, I think, could model much more extensive real-world problems than rigid transformations can. So at the very end, I want to, what is it? Yeah, a bit time. Okay, at the very end, I want to think about to talk about what I want to do in the future. So basically, if you want to realize this generalized robots, like where it works everywhere, we want to achieve that level of generalization. It's a non-existence yet. The only thing that's close to that level of generalization is this linguistic intelligence, this GPT intelligence. That is also very helpful for robots in semantics, high-level planning, in injecting knowledge in natural language interface kind of thing. But what we don't have, this is non-verbal intelligence. It is about the spatial physical understanding that includes multimodal sensing, sense of space, intuitive physics and motor skills, etc. These things they're not easy to be modeled by language, and we are not quite there yet in understanding this in our neural representations. And a typical way today we do this is just by learning this image reaction mappings, and hopefully this thing we'll just talk about will emerge some. But basically what I'm pitching today, what I talk about is that probably 3D model is a 3D world representation is a better substrate for this kind of ideas and concepts to emerge from our systems. But how to do it? I don't think it is just by solving each individual 3D perception tasks perfectly, like solve 3D reconstruction and solve 3D tracking and do this separately is not the way to go, because that is very tedious, and probably before that, it's like we already moved on other approaches. But I think we should find a more unified perspective in turning this real world representation into this native spatial physical intelligence. And so my future plan to go from this raw sensory data to this native spatial physical intelligence has three layers, each building on top of the previous one with more abstraction. The first thing is to perceive the physical world. That is to unify geometry, motion, and interaction. I talked about geometry, I talked about motion, and in physics, we actually estimated interactions. But what I want to put here is that interaction should be treated as a first-class citizen in 3D vision, which is basically non-exist in 3D vision today. But if we can understand this interaction, which is basically forces and why things move, that makes the 3D perception problem causal. And that is the foundation for making it physics grounded. The second layer is basically what I call it or focus on what matters, or task-driven abstractions. Because solving a robot task does not need you to understand everything in the environment. Cleaning up a dish does not need to understand everything in the kitchen, where every bottle is. That is obviously not necessary. But how do we know what is important and what we should understand and focus on? It's probably a minimum word model for the task. It's like what relevant is if you perturb the thing, if you change the state, it will lead to failure, or it will lead to a different outcome. And we should understand those essential things. And these things with this representation in geometry, motion, interaction provides us basically a pool of candidates to abstract from. The third thing is called distill the principles. So the idea is if you learn a policy or whatever, can we actually understand what are the typical strategies the network acquired? That thing is, that is actually beyond just learning to do a task well. And I want to tackle this problem from the perspective of symmetry discovery. The idea is basically extract the structure post hoc. The idea is that we probably don't have a lot of understanding of how real-world symmetry works, like beyond just simple SO3, SA3 transformations. Real-world tasks typically don't have those nice properties. But we do have a lot of intrinsic similarities or lower dimensional manifolds in such problems. And discovering symmetry is one way to recover such lower dimensional structures from this buried implicit problems. One idea is to treat this, for example, we'll have these generative models or autoregressive models as dynamics models. And this PDEs or SDEs, we can learn this like generators that in the latent space, they may which represents the latent symmetries that are discovered by the networks. And these latent structures can help us either reinforce the network for regularization, or they themselves reveals what patterns and rules these networks found. And this is, I think, going forward from building symmetry into network, from recovering symmetries from arbitrary networks is, I think, a very promising direction. And with that, I'll conclude my talk. And thank you all for listening. Yeah.
So for the geometry learning, is there like any potential risk if being more likely to be biased to the noisy data or something.
Be biased to the noise data? What do you mean?
For example, like if you have like data, some kind of outliers, and if you're trying to learn symmetry from the data that contains some outliers, it'd be more like biased to those kind of outliers than like non-symmetry learning.
I see. I think the symmetry, like for example, the symmetry discovery part is like you learn a model, you learn a big model. Like today, what people do, you learn a very big model. They probably already do some task approximately well, like do kind of well. So it's not just trained on those sparse bad data. So you have a network where it kind of understands they have some inherent symmetry, but it's not reliable or it's not formed. They still have some outliers. The idea of discovering symmetry is that you find these symmetries that are this that emerge from these dynamic systems, and then you can retrain this network, fine-tune this network by enforcing such structures. And that actually is used to reduce the outliers, as we just said.
So for the first step, like physics and other like stuff, you mentioned that like the inference is not real time. So what is the main bottleneck that make it?
First, it's like I think there are actually a lot of things that can be improved. I think the first thing is that this structure is just not a unified, like not a joint framework. You do the vision first, and then you take the pose, and then do the physics-based optimization, and then you combine the two. I think ideally the tracking part should already take, honestly, like for example, the tracking is guided by physics laws, and the geometry, you have the geometry from this generative priors. And then when you, for example, in my similar to my second work, when you diffuse, you actually take this physics as some level of guidance before you just finish everything. So putting everything in a joint framework should make it faster instead of just running these multiple loops. And I think just generally speaking, a lot of things that not just this work has. For example, diffusion models themselves can be slower, and optimization themselves can be slow. These are also problems.
Thank you.
For time, let's just think